Okay, so it looks like we have a light crowd today. Can't imagine. So thanks y'all for coming. I appreciate you actually coming in person. Just a quick. We'll start with a quick reminder of what the deal was last time. We were talking about surface integrals. The big idea is sometimes the quantity that you're interested in is accumulating over a surface in space. Not that different from a curve in space. If you think about it, it's dimensionally weird, dimensionally out of place, but still something that we can approximate with a parameterization. So we define a new kind of Riemann sum that adds up over little pieces of surface, for which we have a notation and a name that we talked about last time. We have a strategy for computing it because, after all, this surface over which my quantity is accumulating, I can view it as being the image of a function. Namely, I can parameterize it. And from that parameterization, we can compute various partials and their cross product, and thus this capital N, and thus the stretching factor, and all the details of that we talked about again last time. And therefore, we have a stretching factor to stick in as we pull back that integral. Right. And we talked through an example in which, let's see here, by the way, let me maximize, an example where we get our hands dirty and actually do one. And the details here, again, I'm going to leave for last time where we discussed it. But the big idea is that once you parameterize your surface, and once you go through and do all the algebra, yada, 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 to get your stretching factor, it really is kind of a matter of plugging and chugging, right? So, again, details last time, and then I further pointed out that the details here that were involved in computing mass, total mass that's distributed per the specs above, you can see all those same details right there, right, in the different but kind of parallel computation for the x-coordinate at the center of mass, because you're using the same surface with the same distribution of mass, with the same parameterization, and therefore the same stretching factor. Okay, all right. So likewise with other calculations that you might do on that surface. Okay, things get weird when we start talking about flux, right? Flux is a different quantity, different physical quantity, but importantly, kind of more sort of vector relevant. Our first tip of which being that we have to recognize early on that which direction through the surface I'm talking about matters, right? Because there is a fundamentally different. It's just different if fluid is flowing upward through a surface than if it's flowing downward through a surface, right? So one is obviously the negative of the other. So if you're going to calculate, then you have to decide, well, I have these two things, two different directions through a surface. They are negatives of each other, but which one is intrinsically the one I'm going to call positive? Right? And so that's this idea of an orientation. When you indicate an orientation, namely a unit normal vector, or I should say you might say a family of unit normal vectors, consistently pointing one direction, if you will, through the surface. Obviously, they're not all the same vector. It depends on how the surface curves, right? But if you have one family of unit normal vectors, that decides what we're going to call the positive direction through the surface. So we call that an orientation, this decision about which way should our normal vectors point. Okay. All right. And with all of that, then, chop it up, add it up. But again, wait a second. No, I think this is about where we left off last time. So maybe I better stop going super fast and actually slow down and start talking details. Okay, so reminder then. We were looking at a little piece of surface. We've got an idea in our mind now of which is the positive direction through the surface. Again, it could be either way. It's just a question of what you're interested in. It's an arbitrary choice. decided by the question asker, right? Not the question answerer. And how do I compute the amount of flux of a given vector field through that little piece of surface in the direction indicated by that orientation? Okay. All right. And then, again, chop it up, add it up. So first let's talk about the chop it up, add it up aspect of things. The whole is the sum of the parts. Again, this is my little ritual when I'm doing any question that involves an integral. It makes me feel comfortable to first write down just a, super obvious, nice little freebie kind of algebraic representation of the big point, which is that the whole is the sum of the parts, right? So that's all this says right here, is that the total amount of flux is the sum adding up over all the pieces of the surface of the little pieces of flux through each surface, each little piece of surface. Okay, so for example, this right here, this d phi, that says, okay, how much grand total over that entire piece of surface, how much flux is there? And on this little piece, it's actually a pretty straightforward question. After all, these are little bitty pieces, not to scale, right? This is blown up. This is actually a teeny tiny, itty bitty little piece of surface, right? So on this little bitty piece of surface, it's approximately flat. It's so small, the points are pretty close to each other. The vector field hasn't really had time to change very much, so the vector field's approximately constant. And so on this little piece, we can recover our previous formula where vector field dot normal vector and then times the area ds. Is everybody okay with that? Now, ultimately, just from a strategic standpoint, again, not really that different from computing mass. How do we compute mass? Well, we recognize first that the whole is the sum of the parts, and then we look at any given individual little piece, and then we kind of, figure out what we got to do on each individual little piece. Where it's mass, then it's, density times area. Here, it's flux, and so it's, different formula. All right. So with that noted, ds being, d phi being this quantity right here, that goes there, and we have ourselves a new kind of an integral, pretty much. Let's see here, just to get things out of the way. Here you go. Now, it kind of looks like a scalar surface integral. We wrote stuff down that looked kind of like this, integral over surface. What appears to be the integrand being the ds scalar, representing area of a little piece of surface. What's the difference? And the difference is what at a casual glance looks like the integrand, kind of isn't really. Right? I feel it's reasonable that when we talk about a differential for an integral, the differential represents everything relevant about the piece of the domain. Right? Look back at every integral we've looked at in the past. Right? Starting with a single variable integral. dx tells you how big is that little piece of the domain, and what's inside of the integral is unconcerned about the domain. It exists independent of what your domain is. Couldn't care less about your domain, right? Totally independent. Well, here's the thing. Both n and ds are intrinsic to the domain. ds is telling you the size, n is telling you the orientation, how that piece of area is sitting in space. So, we need to figure out how to rewrite this in a way that actually makes more sense. And I'm going to remind y'all, I'm going to flash back here real quick to vector line integrals. Remember, we were computing work, and W is integral of dW. And then, there's different ways to write this. I'm going to write it first, even though this wasn't our first option back then. I'm going to write it as f dot t ds. Right? Now, again, we came at this chronologically in a different order, so I don't want to worry about that. But this is one of our formulas for how to compute work. But this is not really our favorite way to talk about TDS, right? I mean, T is a unit vector telling you the orientation of your curve. DS is a scalar representing the size of that little piece of curve. And in practice, for convenience, most of the time we'll rewrite this then as F dot, and we'll give this a different name. We'll call it the dx vector. And again, different points of view on how to think about the dx vector, but the point of view I'm going to push here is that dx vector is a vector representing everything you need to know about the piece of domain. The direction is the direction of the orientation. The magnitude is the size of the little piece. That's our dx vector. And here we are, again, with a very similar sort of circumstance. We find ourselves with this integral right here that we've developed, right? Looking at both a vector and a scalar, both of which together kind of represent our little piece of, now this time, surface. And again, one of them, the unit normal, is representing the orientation, just like t was representing orientation. And then the other factor, ds, this represents size, now area. Of course, it's a surface, not a curve. So this is size called area. Just like up here, the little ds was representing size, in that case, length. Right? So in the same way, we're going to lump these together and give these a name and think of this as our real, fully developed sense of what a differential should be for this integrand, for this integrand. So this is my favorite notation for how to write one of these vector surface integrals. Right? Kind of like a vector line integral, and you just have to make sure to remember for computational purposes and other interpretation purposes of what that ds vector is. It's just n times ds. And just a little summary down here. The ds vector tells you about the size and the orientation of your little piece of area. Everybody happy? If you like, it's just notation. But I think it's very natural. Okay, so this noted, how do we actually compute this? Well, we have some details already worked out in the context of working out scalar surface. Oh, I wanted this in highlighter mode. In the context of working out scalar surface integrals, we already talked about how the surface can be parameterized, and that this allows us to take integrals and pull back integrals into the ST plane, and we did a couple of examples. For which purpose we already wrote down this capital N, which was this, and its magnitude is the ds scalar, etc. And with all of that already done, here's how we're going to compute the above. Now, I start by just copying from the previous page. This is all a straight up shameless copy from the previous page. I'm going to point out here that, let's see here, here it is, ds scalar is magnitude of capital N times ds dt. So here we go, ds scalar, magnitude of capital N ds dt, just plugging that in. Now, having done that, I'm going to commit a math crime. I'm going to make the assertion, if you will, that this product right here, I mean, if you think about it, little n is a unit vector pointing perpendicular to the surface. This scalar out here is the magnitude of capital N. Capital N also perpendicular to the surface. So isn't that same direction as little n? And now multiplying by the magnitude, doesn't this make it have the same magnitude? Isn't this just a fancy way of saying a vector that's in the same direction as capital N with the same magnitude as capital N? Looks like a duck, quacks like a duck. This is capital N. Which again, I freely confess, right, that this is a math crime. I just made a big mistake, did it on purpose, right? And I'm going to come back and clarify what the mistake is in just a few minutes. But right now, I'm going to say that the mistake I just made is a little bit of a distraction. I think we should get a win under our belts first, and then we'll come back and deal with the subtleties, right? The little worry. Having made that observation, by the way, when I say this is wrong, it's not 100% wrong. This is mostly right. So, anyway. So notice what we have then is an answer for if you're going to compute flux. We have a plug and chug formula. This is a, take your parameterization, compute your capital N vector. F is computed at x, y, z, which can be written in terms of s and t. Also, everything in this expression is all in terms of s and t. This is an integral in the st plane. Plain old double integral plug and chug. And let's see how that works out. Okay, so we want to compute the flux. Certain vector field given. Surface given. Right, here's our vector field. Here's our surface. Let's see, it's the portion of the paraboloid there sitting above the unit square in the xy plane. And how am I going to compute that flux? Okay, well, I'm going to, of course, use this formula right here. Let me get rid of all this distraction. I'm going to use this formula. If you want to compute flux, here you go, F.N dSdt. Let's write that down. Now, in order to do that, of course, I'm going to have to take my parameterization. Notice I'm using the graph parameterization here. Okay. I'm going to take my parameterization. I'm going to take the appropriate partials. It's a little calculus. I'm going to take the cross product. A little annoying, a little algebra. And there's my capital N vector. Notice how nice is this? I don't even have to compute the magnitude of capital N, right? You look at our formula here for flux. It doesn't say in this final expression, it doesn't say anything about the magnitude of capital N. That's only if you're doing scalar surface integrals. With vector surface integrals, it's just capital N itself. The magnitude's inside of there. It's part of what we needed. It helps us understand our ds scalar. But it's already wrapped up in there. I don't need to separate out the magnitude. It's very, very convenient. And so with that all computed, then here again is our formula for flux. Flux is this expression, which simplifies like this because, after all, our vector field, notice that our vector field is written in terms of x, y, and z, but x, y, and z are given in the parameterization. So this is just the kind of the plugging in and pulling back thing. So specifically, when I need to write z, apparently, as one of the first things to do in pulling back the vector field. Oh, z, I can see it right here. There it is. Z is s squared plus t squared. That's just plugging in. Likewise, what about this x here? Okay, well, x apparently is s. Likewise for y. Is everybody on board with that? Plug and chug? I love it. Yeah.
How do you know that vector is in the right direction?
Oh, yeah, I'm going to get to that in a minute. Yeah. No, it's a great question. Fantastic question. Okay, so there's our vector field, and again, borrowing the formula from above for what capital N is. Here it is. Capital N is that. And we're done, and we have ourselves a double integral, and off we go, plugging and chugging. Is everybody all right so far? Modulo, your excellent question. All right. Okay, so when we've talked about different, vector line integrals, scalar line integrals, scalar surface integrals, previously discussed, we always ask the question, does the parameterization matter? So natural question to be asking here, does the parameterization matter? And the short version is not really, but kind of. And just like with it's just like with vector line integrals, it's about the orientation. So you put your finger right on it. So just a reminder, again, here's our setup. We've got a surface given. We then parameterize the surface. And blah, 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 compute various stuff. Here's the thing you have to be aware of and you have to be sort of, cognizant of. Our domain is not just a surface, right? And you can see it in our development that we wrote originally. Our domain is an oriented surface. We have to know which direction through the surface we're talking about. So, when I say that our domain here is a surface, not really. Our domain is an oriented surface, and it's going to be oriented one way or the other. Now, which way? What's the right way to orient this surface? There is no right way. There's just which one are you interested in? Neither one of these is intrinsically positive. Some people tend to think up is intrinsically positive. It's not. Why would it be? Right? I mean, after all, if up were intrinsically the positive, then if it were slightly tilted surface, then I guess that would have to be intrinsically the positive, which, et cetera, knee bone's connected to the leg bone, et cetera. Does that mean that to the right is intrinsically positive? And what if I take my allegedly intrinsically positive and kind of turn it the other? Now, does that mean both? Where's the line between this one and this one? Right? This is all made up. It's all arbitrary. Right? So when somebody asks you a question about flux, they need to tell you, and if not, you need to clarify, which direction do they consider to be positive for the particulars of their circumstance. Right? And it's just, it's kind of, whatever they want it to be. Now that said, when you parameterize the surface, we've got a parameterization that we come up with to kind of trace out all those points to kind of manufacture the surface. But when you do that, that dictates what your partials are going to be. And that dictates what your normal vector, capital N, is going to be. And that effectively dictates the little n vector that you're going to be using in your calculation. Right? So this is a weird circumstance. There is a given part of the question, namely what direction is this surface oriented as stated in the question, and then you basically arbitrarily make up, coin flip, a parameterization that's going to decide on which direction you're going to call the positive direction through the surface. And no fair. You can't just make up your own orientation. Does everybody see the kind of the difference? So there's an analogy here to something we've seen before. We didn't really talk about it because this wasn't a problem particularly. But if I have a curve, here, for example, is a curve, and maybe this curve between those 2 points, I want to know how much work does it take to move along this curve? Well, which direction are you going? Right? Now, I can parameterize this curve a bunch of different ways, but fundamentally, if I parameterize the curve this way, then I'm going to have an answer to the question of how much work does it take to move that direction along the curve. On the other hand, if I parameterize the curve this way, then I'm going to get an answer to the opposite question of how much work does it take to move that way along the curve. And they're just not the same. How do we tell? In the curve example, it's pretty straightforward. You just kind of look at your parameterization and where is t equals 0 and where is t equal to 1, and you just look and see which way you're going along the curve. It's usually pretty geometrically clear. After all, if we're parameterizing a curve, we think of our parameter as being time, which kind of intrinsically suggests a motion that you can imagine. You can almost see the motion as part of what your parameterization is. And so this issue is kind of a non-issue in the curve case. Just make sure you're going the right direction. Issue over, right? And deep down, ultimately, the same kind of thing is happening here. It's just so much harder to see. Right? But in the same way that when you parameterize a curve, you've already, from the parameterization itself, you have indicated an orientation intrinsically. Well, likewise, when you parameterize a surface, even though you can't see it because there's a lot of algebra to work out, it's not particularly intuitive, but when you make a parameterization, you are intrinsically putting an orientation on that surface, and you got to make sure that you parameterize it the right way, not the wrong way. Does that make sense? So this is the resolution of my math crime, right? A reminder. So the copying from the previous page. This is the math crime. Again with the, I need to be in highlighter. I put this asterisk over here. Crime to be revealed later. And here's the crime. Just to say it explicitly, I was asked a question where there was a given orientation, given in the statement of the question. And then I completely ignored that. And I made up my own parameterization, thus leading to a capital N vector, which, to be fair, is a unit normal times a magnitude. Yeah. But all of this came, the direction that this points came from the parameterization, not from the statement of the question. And I just, on the previous page, I just baselessly asserted that this direction and that direction are the same. And that was absolute nonsense. Is that cool? Right? All right. So, good news. The only possible difference between these two vectors is a -1, which either they're the same, in which case there's no problem, or they're the exact negatives of each other, in which case our answer is just off by -1. So, so roughly speaking, the advice on this is going to be parameterize any way you want. Don't even worry about it. Just parameterize. It's good. It's cool. Whatever. Any parameterization. And then subsequently, after the fact, take a look, see if you did it right or wrong. And if you did it wrong, then just throw a minus sign on there. Example to follow. I'll show you the specifics in a second. Okay. All right. So that is the nasty issue, and why we see it in surfaces but not in curves. So just a reminder, we previously had ds as n ds dt. Again, math crime included in that equation, and now I'm going to fix that by putting in the recognition that we have to worry about the minus sign. So ds might be in du dv, but it might not. Possible minus. Is everybody okay? All good? Okay. All right. So let's see an example, and in this example I'm going to show you how to tell after the fact. Did I do it right? Did I do it wrong? You'll notice in the statement of this question here, it's the same vector field. We're still computing the flux, the same paraboloid, the same portion sitting above the unit square. It's exactly the same except for one little detail. I am this time parametrizing it downward. Free country. I can ask any question I want. Again, there's nothing magic about upward, right? I can orient this surface any way I like. I'm going to orient it downward. Just because. Okay, so how are we going to proceed on this exam? How are we going to deal with this downward business? Step one, don't worry about it. Step one, parameterize, however might be most convenient. I like the graph parameterization. I'm going to use the graph parameterization. I encourage you as well. You take the partials, you take the cross product, there's your capital N vector. And now here's where you have to pause, right? We need to draw a line, take a pause, and ask this question. Oh gosh, ask this question right here. Now, I was given an orientation. I was told that I'm supposed to orient my surface downward. I parameterized, and implicitly, in ways that I can't tell at a glance, I've already selected an orientation, and not clear what it's going to be until you write down your capital N, and now you can see that, in fact, inadvertently, we have parameterized with a positive z coordinate, which means, if anything, this is upward, not downward. Right? So comparing these, yep, I screwed up. Now, again, this is the method that I encourage. I'm not saying I've done something that I shouldn't have done. I'm just saying, well, look, this, I'm going to parameterize as I will, and then when I identify after the fact that I've parameterized the wrong way, then I'm just going to fix it and say, whoopsie, and just put a minus sign in there and carry on. Does that make sense? Okay, and that's all you have to do. On a test, now what you can't do is just put a minus sign and leave it at that. Right? You have to give me some indication of where that minus sign came from. Right? So one thing that I think would be a perfectly reasonable documentation of your reasoning, and then let me just get rid of all the rest of this just to be clear. If you were to just circle this is plus and that says downward, and if you were to then just draw an arrow, full credit. To me, this is very clear, right? You're indicating, I think, plenty clearly enough that minus sign you've inserted was not just because of no particular reason, right? That minus sign came from what is very clearly, as you've indicated here, a comparison between your inadvertently chosen orientation and the prescribed orientation. Plenty good enough. Yes?
Will it always be looking at the z coordinate?
Nope. Another great question, and I'm going to get to that in just a minute. Yeah. In this case, upward or downward is going to be determined by that, and I'll elaborate more on that in a second as well. Yeah. Okay. And then, everything else is plug and chug, and so I'm not going to repeat those details because that's all pretty much the same. I do want to say a little bit about how students write this. We are stuck with certain things. We are stuck with that once you have a parameterization, what the partials are is what it is. That's not negotiable. The partial derivatives are partial derivatives, period. Right? What the cross product is, that's not negotiable. That is explicitly what it is. So what you can't do, and it would be a mistake to do, is to notice this inconsistency and then put a minus sign inside of your formula for the normal vector. Like if you were to just stick a minus sign right there, no, you can't do that. Capital N is defined as xs cross xt. And again, I remind you, a lot of people will say it's going to have the same effect. It's going to be a minus sign in your answer at the end. We're not interested in the answer at the end, right? I know you've heard me say this a million times. It's not about the answer at the end. It's about whether your reasoning is valid. Capital N is not the negative of what it's defined to be. And that's just wrong. It's effectively two minus signs because you would you'd have an incorrect formula for your capital N, and then you would have an incorrect statement about the relationship between the ds vector and capital N. And yes, two minus sign mistakes is an even number of mistakes, but it's still two mistakes. Is everybody on board with that? I mean, again, it can't emphasize enough. This is relevant to the reasoning, not the answer. We don't care about the answer. All right, so let me be clear, crossing that out. Yeah. Okay. All right, so how do we interpret the language? How do we choose language to talk about orientations? We have to make a concession, and that is that we're not going to be able to have precise language to describe orientations. It's too much trouble. For example, what word describes precisely with no inaccuracies exactly which direction all of those green vectors are pointing? Exactly what direction? Is there a single word? No, of course not. That's ridiculous. Right? It's not. That's just, we don't have such words, right? I'd have to write out an explicit formula for them. That'd be the only way I could actually be precisely, exactly describing the directions. And likewise, there's no single word to describe these directions. And these are my two options. If I were going to put an orientation on this bowl surface, an orientation would either have to be the green vectors or the blue vectors. Right? So precise, we're not going to do. What we're going to do, our goal here, we don't need to be precise. We'll be precise later with the formulas. That's what formulas are for. With language, what we want to do is simply to be unambiguous. Right? I need to make a clear distinction between these two options. And let's look at our language choices. If I were to say upward, which of these two orientations might I mean by upward? And I'm going to point out that all of these green vectors are at least somewhat upward-ish, kind of, right? They're not pointing downward, they're pointing upward, right? All of the green ones are at least somewhat upward, and none of the blue ones are in any sense upward. So if I say oriented upward, there's really only one reasonable interpretation, and that is that I mean the green orientation. Does that make sense? Yeah. So it's about being unambiguous. It's not about being precise. Okay, downward, of course, would be the blue one. Now, there is another language choice that some people like to work with, and they like to say inward versus outward. The idea being that this is like a bowl of cereal, and the green vectors point in to the bowl of cereal, and the blue vectors point out of the bowl of cereal. The green vectors point to where you want the milk to be, and the blue vector points where the milk really better not be. So, fine. The problem with that point of view is that not all paraboloids contain cereal, right? What if it was like a gas or something, and it can kind of float around in any direction? In fact, there is no well-defined inside of that surface. It doesn't close up. It doesn't contain anything. Right? Yes, you can hold cereal, but you cannot hold butterflies. Does that make sense? Did I see that? No? Okay. Now if you say inward versus outward, I would kind of know what you mean, so I guess. But this is clearly an inferior choice, and I advise against it when there's a perfectly, clearly much better option right here to distinguish these orientations. Now, on the other hand, I am not saying that those are the only words to use. It depends very much on your surface. So, for example, if we look at this surface here, then again there's two possible orientations. There's the, again, I'm going to use colors for convenience. There's the, what you might call the blue option, and then there's the green option. And you know what? Upward versus downward here would be a pretty bad choice of words, wouldn't it? Right? If I were to say upward, which one of these orientations is upward? Is that me? No. Okay. Is the green one upward? I mean, they're pointing upward along in here. Well, yeah, but they're pointing downward along in here. And worse, some of the blue vectors point upward too, right? So upward does not clarify. This is majorly ambiguous. And so this is a bad choice of words. Whereas in this case, there really is truly an inside, right? Sorry. The blue one is unambiguously inward. The green one is unambiguously outward. So here, that would be the appropriate language. So always tailor your language to the geometric specifics of the surface situation that you find yourself in. Don't just marry yourself to one choice of words or the other. Yeah.
So given an example with, like, let's say like a sphere like that, and you were to say like inward, what coordinate would we look at in our vector?
Yeah, right. Okay, so what you'd have to do is get more specific. So depending on where this surface is, I mean, it might be convenient to look at, the North Pole, maybe, and then just think about what, and how the question is phrased. It could be, there's a lot of different ways it could be phrased. It might say oriented in such a way that, the normal vectors are given by the following formula, in which case you'd have to plug in and see what the vector is at that point and then interpret accordingly. Or it might be described in some other way. I've done some questions where I say, at the following point on the surface, the orientation vector is specifically a certain vector. Yeah, and then again, you have to do the geometry, right? There is no algebraic way around this. You'd have to identify, okay, wait, where is this point? Which direction is it pointing? And is that inward or outward? Yeah. No worries. Yeah, and you can find some of those on my old tests. Let's see if I can. So third example down here, I'm going to let y'all mostly read this one. Depending on the circumstance, again, just kind of think carefully. I think the best way to do it here is to notice that looking in the y direction, each of these orientations is either entirely in the positive y direction or entirely in the negative y direction. And upward and downward doesn't make any sense at all. All right. Okay. So as usual, I mean, there's some good fortune to keep on the lookout for. This is where life gets good, right? With non-lucky scenarios, you plug and chug, and we've already talked through the plug and chug pretty explicitly, right? So let's look at lucky coincidences. Here's one. By the way, spheres are, if you ever see a sphere, it's not a guarantee that there's going to be some massive good luck like this, but it's worth eyeballing, right? Spheres are loaded full of symmetries, and that's awesome, and that makes good things happen. So stating the question just bluntly, we got a surface, we got a vector field, compute the flux. What method you should use to do this is not given. That's your problem, right? So decide which tool to use. Now you could parameterize, and that would be fine. The problem is that if you parameterize, your parameterization is going to be full of trig. Right? You're going to use the spherical graph parameterization. There's trig everywhere. Each of these x, y, and z is full of trig. It gets a little hairy, right? So what's nice, though, is that you can avoid all that in this case because among our formulas for flux, we have this one, and I can see exactly what my unit normal vector is using a trick not unlike what we saw in an example some time ago. The unit normal vector, thank you spheres, you got to love spheres. Unit normal vector is just a scalar multiple of your position vector. This is sphere centered at the origin, of course. So let's see, this radius was 3, so I mean, I can't say n equals x itself because I need this to be a unit vector, so I divide by the radius. Now it's a unit vector. So you write that down, and we have our vector field here. Now, I haven't pulled back or anything, right? I haven't plugged in and rewritten everything in terms of S's and T's and such, but just kind of recopied it, and now, casual glance, dot product is 0, we walk away. Is that cool? So, heads up, right? This will make your life easier. Again, this kind of thing came up a lot in physics long ago, so I think it's going to come up a lot for y'all in engineering as well. Well worth every time you see a flux question, just where's my good fortune? What's awesome about this that I'm given? And then look for the possibility that good stuff will happen. Here's another example. Weirdly described surface. Y'all can read the specifics there. What scares me the most is this right here, and I'm thinking, yikes, wow, that's a weird relationship. I don't know, like fourth powers, I'm afraid that's going to find its way into the bounds of my integrals, which means I'm going to be, oh my God, the integral sounds like it's going to be horrifying, right? So let's look for a convenient way around. The convenient way around is that my surface is entirely contained within a plane. This may be a weird and ugly shaped surface, but it's flat. And that comes with two benefits. For one thing, it means that literally for my entire surface, y is equal to 3, which means that literally for my entire surface, the second coordinate of the vector field is 0. And that just made some of my ugly disappear in the formula for my integral. The other thing, very convenient, and again, immediately as a consequence of the fact that we're looking inside of this plane, I can instantly write down exactly what the unit normal vector is, right? This whole surface, weird though it is, it's all in that flat plane perpendicular to the y-axis, and so easy normal vector. Let's doff the cap to the fact that this says right here positive y direction, so thus the positive 1 instead of negative 1. Didn't have to parameterize anything. And again, plugging that in gives me zeros there and there. And again, the whole dot product 0, we walk away. And all this ugliness, all this horrifying nightmare of that we might have had to deal with, not our problem. Whole thing 0. Done. Is that cool? Again, we're going to be on the lookout for this kind of thing. This is an underappreciated, very valuable trick in computing these kinds of intervals. And let's see, how are we doing? Let's see here. How much time do we have left? We have 2 minutes. You know what? I think this is I'm sure I owe y'all 2 minutes. We're going to draw the line right there, and we'll pick up here on Monday. So happy Thanksgiving, y'all. Have a good break. See you in a week.